shared PowerPoint. Carol sends the shared
Ah,
screen.
yeah. It's
Oh,
perfect. It's very clear.
okay, nice. I will start my presentation. Hello, everyone. Today I will give a report on this seminar, and the title of the report is Revenue Sharing or Membership versus Right Sourcing Drivers, Model and Evidence. I'm Wang Hao, a PhD candidate from School of Economics and Management, Beihang University. My advisor is Professor Haijun Huang. This working paper was conducted under the guidance of Professor Tianliang Liu and Professor Haijun Huang. So, my presentation contains 5 parts: introduction, literature review, model setting, theoretical analysis, and data-driven part. First, the introduction part. I will introduce the background of the research. So, ride sourcing platforms such as Uber and Didi have received the taxi market by online matching passenger and drivers using advanced information technology. With the emergence of wireless communication tools, the global position system, and powerful mobile apps, these ride sourcing services provide significant improvements over traditional taxi systems in terms of reducing taxi crossing time and passenger waiting time. Traditionally, the ride-hailing industry has been dominated by street-hailing services. In the traditional taxi market, the driver and the taxi company are in an employment relation. The driver will regularly pay a certain amount of money, membership fee, to the company, and the company will provide the driver with services related to vehicle operation procedures, insurance, repair, and maintenance. By contrast, drivers registered on ride sourcing platforms do not need to pay membership fees to ride sourcing companies or platforms as a price for certain qualifications, but instead sell a defined percentage of its order with the platform, which can be called the revenue sharing tax scheme. The table below shows the driver commission structure for traditional taxi markets in different countries, and the driver commission in ride sourcing markets in different platforms. So change from traditional membership fee cards to revenue sharing one not only affects the income and revenue of drivers and operators, but also profoundly affects the driver behavior or work behavior of drivers. Ride sourcing drivers can truly free choose their working hours, whether to work, and the length of working hours. This flexibility makes the labor supply in the market more flexible. In reality, the commission of ride sourcing have become a higher level and thus criticized by the public. Exciting studies give less consideration to the impact of different sourcing schemes, supply side, in ride sourcing market. So next comes the literature review. Our work falls within the research area of operations strategy in on-demand service market. As the sharing economy become more prevalent and prominent, a growing body of literature have provided insights into operation management strategy of two-sided market, which often cites the right sourcing market as a typical example. The platform as an intermediary optimizes the price offered to riders and the waste paid to drivers. Unlike a traditional supply chain, the platform indirectly manages independent self-cycling contractors through visits. Example of issues invested above uh, include should the platform adopt dynamic pricing or static pricing, how to implement such pricing in different settings, and the profit impact and welfare effect of implementing such pricing, and how to optimize price of it when passenger is delay sensitive and driver is weight sensitive. Uh, the price and weight of on-demand service market are the core decision variable of the platform. Different from this study, our work characterizes the relationship between different commission structure and driver supply behavior. Another important literature stream is related to our paper is previous work on nonlinear pricing in the surface pricing field. Casson and Feldman analyzed whether a company should choose to charge on a per-use basis or sell subscriptions when its service has consistent effect. Wang, Lindsay, and Yang explored the incentive for a profit-maximizing toll road operator to adopt some simple nonlinear pricing scheme when there is congestion and collecting toll is costly. And a lot of research has focused on the demand side of subscription versus pay-per-use, or the use of nonlinear pricing, which has been published in leading service science-related journals. One critical difference between our work and this research above is that we model the nonlinear pricing was structured on the supply side. Moreover, we conduct our research in a typically two-sided market, while the above study is focused on the demand side only. Next, we will into the main content of the research. First, model setting. We defined the demand function as a decreasing function D of price and waiting time. The price P is exogenous and determined by the monopoly platform, and the waiting time or delay T, capital T, is endogenous, which is determined by driver supply and passenger demand at equilibrium. We model the individual supply function. The amount of time an individual driver is willing to work for the monopoly platform can be expressed as a function of its toll, realized demand, and reservation income X. And we assume the realized demand N reflects the indirect network effect of demand on the supply side. The increasing number of consumers on the platform will positively affect the driver's willingness to work. The result is determined by the monopoly platform. The heterogeneity of reservation income means different drivers choose different amounts of work time, which is consistent with practice. As Uber reports, 53% drivers work 1 to 15 hours per week, and 5% drivers work more than 50 hours per week. Based on the individual supply function, we could calculate the produced supplies for drivers with reservation income X. If the platform imposes a membership fee, each driver will decide whether to enter the market based on the relative size of their produced supplies and the membership fee. So the membership fee charged by the monopoly platform is equal to the produced supplies of marginal driver. So the upper limit for the type of driver participating in the market could be expressed as this equation. And the total supply of the market is the integral of working hours worked by drivers participating in the market. And in the sphere of analytical works, considering delay function for ride sourcing platform markets, there are at least 3 research streams. We use N to respect to demand and M respect to supply. And W is the delay function of demand and supply. The fourth stream includes delay function form estimated from steady state queuing theory. The second stream describes the waiting time based on 3 driver rates: states, ideal, en route, pick up, ideal drivers, en route drivers, pick up drivers. These 3 parts add up to the fleet size N. The third stream is more like a simplification of the first stream. Only use the utilization rate or the difference between supply and demand. Next, the passenger's waiting time can be expressed a function of realized demand and realized supply. We will focus on a generalized model and consider the delay function with special properties, wide good chases case, or approximate reduced form in the excitation section. We assume The delay function is differentiable and it has the following derivative properties as follows. The general equilibrium equation system with three decision variables can be expressed below. Although there are three decision variables in the general equilibrium equation system, there are only two decision variables in a single sizing model. In revenue sharing setting, platform determines the price P and weight tau and drives revenue from each completed demand N. So the profit equation can be expressed as this. In this setting, the platform does not set the membership fee, so A equals 0. In membership fee setting, platform determines the price P and membership A, and drives revenue from drivers participating in the market. In this setting, the platform does not charge a fraction of price in each order, so the P equals tau, and the profit equation can be expressed as this. Next, the equilibrium of the model will be analyzed next. In the case of market equilibrium and revenue sharing case, the analysis of the variation of demand, supply, and upper limit of drivers with decision variable is trivial and clear. Under the setting of membership fee, the platform would no longer charge a percentage from each order, so the price charged to passenger is equal to the weight paid to drivers. Each derivative contains two terms under the revenue share case. This setting would make the variation of demand, supply, and upper limit with price less clear and trivial. But by analyzing the forms, we can get at least proposition 1. In the membership fee setting, the marginal decrease in equilibrium demand, supply, and upper limit caused by a unit increase in price in the right sourcing market is less than in the revenue sharing setting, which means under the membership fee setting, the reduction in demand, supply, driver up limit from price increases is reduced compared to the revenue sharing setting. However, the sign of derivative are still undetermined. The sign of derivatives depend on the reaction of supply and demand to the same price. It may even be the case that as the price increases, so does the equilibrium demand, supply, and driver sum limit. We take the derivative of demand with price at equilibrium as an example to check which factor does the sign relate to. So the equation above features 5 electricities and 1 ratio. The electricity demand to delay, supply. And this is worth to noting that when pattern contains for two parts. First part is per unit time width divided by per unit charge, and the second part equals minimum level of supply granted and divided by extra supply. The second part equals 1 when drivers are home drivers. It is worth mentioning that when passenger congestion percentage is 0, the equation is obviously negative because it only had the item f. Next, taking the partial derivative of both sides in equation 1 with respect to membership A, we can determine that the derivative of demand with membership A and the derivative of supply with membership A are negative. But the derivative of upper limit of driver with membership A is undetermined. This is interesting because increasing the membership fee charge does not necessarily reduce the upper limit in the driver participating in the market. This depends on indirect network effects and the reduction of supply to delay. It's the item 3 multiplied by item 4. Next, we will focus on the problem of platform optimal decision-making problem with the goal of maximizing profit. Taking the derivative of profit equation with respect to price P and with tau yield the first order condition. We can find that first expression is the standard monopoly market pricing form, a market markup that is inversely proportional to the price elasticity or demand. If atom Z equals 0, and when atom I equals 0, the fourth expression can become a multiple market pricing form with congestion on the demand side and fixed capacity on the supply side, which can be seen in these two papers. And next, we will take the derivative of profit equation with respect to price P and membership A yields the first order condition and the membership fee chart. Next, the first expression means optimal price per unit time equals period charge membership fee divided by work time of marginal driver, minimum working hours of any driver entering the market, and multiplied by an electricity multiplier. Second expression is a standard markup that is inversely proportional to the driver upper limit electricity of membership fee if B equals 0, which means passengers are insensitive to the conductor. So after the analysis of the two basic pricing instruments, revenue sharing or membership fee base, we consider the non-neutral and manual which employ both instruments further. And the two-part pricing model, while the platform sets the membership fee, it also takes for the percentage revenue for drivers entering the market. It means that A doesn't equal 0 and tau doesn't equal P. The platform maximizes its profit by choosing the price, width, and the membership fee, making a trade-off between the two revenue streams. Platform optimized model and the two-part pricing scheme can be expressed as this. Under the manual pricing model, each driver can choose between revenue sharing charge and membership fee charge. For drivers with higher expected reservation income, it would be better to accept revenue sharing charge. And for drivers with lower reservation income, it is better to accept the membership fee charge. It is worth noting that we assume the passenger driver mass is assumed to be identical, regardless of membership fee charge or revenue sharing charge. And in the membership fee processing, we need to determine two upper limit of drivers. And the one is the type indifferent between paying the membership fee and paying the commission. And another is the type indifferent between entering the market and not entering the market. To enhance analytical trackability and compare the advantages and disadvantages of two basic pricing structures, a simplified model and some assumptions are adopted. We have this simplified assumptions and use an approximate delay function previous mentioned. The important setting is that we let the price externalize and focus on different effects of setting weights and setting membership fee. Based on such models and assumed analytical solution can be get, but limited by space, we only present the analytical results and figures. We vary two important parameters, alpha and C. The alpha is driver sensitivity to weight. The C is passenger sensitivity to delay. So we will focus on how platform profit and driver income change as the price change. We have three main observations. First, low price revenue sharing is dominant. High price membership fee is dominant. And second, while driver sensitivity to weight increases, the threshold price PS, the price that equalizes the profits of two schemes, decreases. It can be found this. And the profit increases, which can be, it also means the market is expanding. We can find in this. Okay. While passenger sensitivity to delay increases, the threshold PS decreases. It is the same like the former case, but the profit decreases. That means the market is shrinking. And next, we will analyze the fleet size. When passenger sensitivity to delay and the driver sensitivity to weight increase, the C and alpha increase. There are three scenarios for the two pricing scheme. First case, the fleet size and the membership fee is always larger. Second case, low price revenue sharing is dominant. High price, the membership fee is dominant. The threshold price is this price. The fleet size and the third case, the fleet size and the revenue sharing is always larger. So the last part is the data-driven part. We use a research data set from the DD Open Data Program. This data set contains the driver trajectory data, 1 billion coordinate data points over GPS trajectories sampled at a frequency of 2 to 4 seconds, and passenger order data, 7 million ride requests or records in a local area of Chengdu, China from the 4th November to the end of November 2016. Here are some statistical stats, and some of the statistical data are estimated based on realistic setting. So we want to explore the impact of membership fee on the extra ride sourcing market, but the extra ride sourcing market has revenue sharing. So we conduct a counterfactual analysis based on a simulation environment. Our simulation environment contains three parts: passenger demand, driver supply, and platform match. We simulate a typical day from historical data by rewinding real happened orders in this state as demand. And for driver supply, we classify drivers part-time or full-time and estimate different statistical models, losses or wells for their working hours and earnings. In the dynamic simulation environment, the income and working time of each driver are counted in real time to determine each individual work decision, whether to continue working next or quit. And for the platform matching, we use a combined weight function, instant reward plus future state value, by pattern eta graph matching, following the pioneering work of using reinforcement learning to assign orders. We based on the value function of reinforcement learning. We estimate or simulate the matching algorithm of real platform. Due to time constraints, we will only present one comparison between revenue sharing and the manual processing. The platform profits first increase, then decrease. There exists an optimal membership fee and the manual charge. And for the platform, the manual charge is always better than the revenue sharing charge. Moreover, the distribution of working hours of drivers and the manual charge has shifted to the right compared to that and the revenue sharing charge. Okay, thanks for your attention. Welcome your comments.
Thank you for your presentation. Is there any questions